Cement is one of the most commonly used materials in construction, yet many people don't realize that cement and concrete are not the same thing. In fact, cement is a key ingredient in the production of concrete, alongside water and aggregate. The journey to making concrete begins with producing cement, the essential binder that holds water and aggregates together. While concrete is the finished product we see in buildings and infrastructure, the process of creating cement involves intricate methods that blend ancient techniques with cutting-edge technology. Although there are many types of cement, the most widely used is ordinary Portland cement, named by its inventor because its color resembled stone from the Isle of Portland in Dorset, England. Raw material extraction and preparation. The story of cement begins deep within the Earth's crust, where the primary raw materials, limestone and clay, await extraction. These materials are typically obtained from quarries through blasting or using heavy machinery to extract them from the Earth's crust. The limestone provides calcium oxide, which will become the backbone of our cement, while clay contributes essential elements like silica and alumina. In regions where limestones of sufficiently high lime content aren't available, some process of beneficiation can be used. Froth flotation will remove excess silica or alumina and upgrade the limestone. Though this is a costly process and is used only when unavoidable. The extracted materials are transported to the crushing plant by trucks, railway freight cars, conveyor belts, or even ropeways. In some cases, they can be transported in a wet state or slurry by pipeline, making the transportation process more efficient and environmentally friendly. The primary crushing phase. When the raw materials reach the crushing plant, they undergo their first major transformation. Large crushing machines break down the quarried rocks into smaller pieces, roughly the size of gravel. This crushing is often done in 2 stages to ensure proper size reduction. The crushed materials then move to the grinding phase, where they're processed in rotating, cylindrical ball or tube mills containing steel grinding balls. This step is crucial because the smaller the pieces, the more efficiently they can be processed in later stages. For softer materials, the breakdown process is different. They're vigorously stirred with water in wash mills, producing a fine slurry that passes through screens to remove any oversized particles. This attention to particle size is important for the efficiency of subsequent chemical reactions. Raw material blending and mixing. After crushing, the materials enter the mixing phase, where they're combined in carefully controlled proportions to create what's called the raw meal. The chemical composition needed for a specific cement is roughly determined by carefully selecting and controlling the raw materials sent to the crushing and grinding plant. Finer control is achieved by drawing material from 2 or more batches containing raw mixes of slightly different composition. In the dry process, these mixes are stored in silos. Slurry tanks are used in the wet process. Quality control experts constantly test this mixture to ensure it has exactly the right balance of ingredients. The raw meal is then transferred to a mill consisting of a large rotating cylinder. Inside this mill, the raw materials are ground into an incredibly fine powder, enhancing the efficacy of subsequent chemical reactions and ensuring uniformity of the raw meal composition. The preheating process. The powdered raw meal then moves to a preheater tower, where hot gases from the kiln are used to begin heating the material. As it moves through the preheater, the raw meal undergoes partial calcination, a process where the carbonates in the limestone start breaking down to form calcium oxide lime. This preheating stage is crucial for energy efficiency as it uses waste heat from the kiln to begin the chemical transformation process. The preheated and precalcined raw meal then prepares to enter the heart of the cement-making process, the rotary kiln. The kiln, where chemistry meets heat. The rotary kiln is where the most significant transformations occur. This massive cylindrical furnace, which can be up to 200 meters long and 6 meters in diameter, rotates slowly on an axis slightly inclined to the horizontal. The temperature inside reaches an astounding 1450 degrees Celsius, hotter than most lava. At these extreme temperatures, the raw materials undergo complex chemical reactions and sintering, resulting in the formation of small, marble-sized nodules called clinker. The clinker consists of calcium silicates, aluminates, and ferrets, the compounds that give cement its strength. The fuel for firing may be pulverized coal, oil, or natural gas injected through a pipe. Some form of heat exchanger is commonly incorporated at the back end of the kiln to increase heat transfer to the incoming raw materials and reduce heat loss in the waste gases. Clinker, cooling and processing. After formation, the hot clinker needs to be cooled quickly and efficiently. It passes through a clinker cooler where air is blown through it to reduce its temperature. This cooling process is key for several reasons. It maintains the clinker's quality, prevents undesirable crystal formations, and allows the heat from the cooling process to be recycled back into the system, improving overall energy efficiency. The clinker may be immediately ground to cement or stored in stockpiles for later use. Dust emission from cement kilns can be a serious environmental concern. In populated areas, it's usual and often compulsory to fit cyclone arresters, bag filter systems, or electrostatic dust precipitators between the kiln exit and the chimney stack. Final grinding and cement formation. The cooled clinker then moves to the final grinding stage, where it's combined with gypsum and other additives in cement mills to produce the fine powder we recognize as cement. The gypsum plays a critical role in controlling the setting time of the cement. Without it, the cement would harden too quickly to be useful in construction. The grinding process can be either open circuit, where material passes straight through the mill, or closed circuit, where coarser material is separated and returned to the mill for further grinding. Sometimes a small amount of grinding aid is added to the feed material. Throughout this entire process, cement plant laboratories check each step through frequent chemical and physical tests, ensuring the final product meets all industry specifications. Quality control and testing. Quality control is essential in cement production. Various tests are conducted to ensure the cement meets national and international standards. These tests control the fineness, soundness, setting time, and strength of the cement. The fineness is typically measured by determining the rate of passage of air through a bed of the cement. Soundness tests involve subjecting the set cement to boiling water or high-pressure steam to ensure it won't undergo any appreciable expansion that could disrupt mortar or concrete. Setting time tests distinguish between initial setting time, when the mix loses plasticity, and final setting time, when the set cement has acquired sufficient firmness. Strength tests are usually made on a mortar composed of 1 part cement to 3 parts sand, mixed with a defined quantity of water. Storage and distribution. The finished cement is stored in large silos until it's ready for dispatch. Modern cement plants use elaborate pneumatic systems to transfer cement from the grinding mills to these storage silos. From there, the cement is either packed in paper bags for smaller quantities or loaded directly into bulk carriers for larger orders. The packaging process is highly automated, with machines precisely weighing and filling bags to ensure consistent quantities. During storage and transport, it's necessary to protect the cement from moisture, as premature exposure to water can trigger the hardening process and render the cement unusable. Environmental considerations and future developments. The cement industry faces significant environmental challenges, particularly regarding CO2 emissions. It's estimated that cement production accounts for 4 to 8% of global carbon dioxide emissions, making it a major contributor to climate change. The industry is actively working on solutions, including increasing energy efficiency, replacing fossil fuels with renewable energy, and developing carbon capture and storage technologies. Moreover, novel cements and alternate formulations that reduce the need for clinker are being developed. Some companies are even exploring completely new approaches to cement production that could dramatically reduce carbon emissions while maintaining the strength and durability that makes cement such a crucial building material. From the moment cement leaves the factory, it begins its remarkable transformation into the structures that define our world. Every day, countless construction sites across the globe combine this powder with water, sand, and aggregate to create concrete, the material that shapes everything from neighborhood driveways to the world's tallest buildings. The scale of cement production is simply staggering. Each year, the United States alone produces enough hydraulic cement to generate $64 billion worth of concrete construction, while globally, the concrete industry has grown into a $1 trillion giant. Whether it's being poured into massive dam projects or helping build the highways that connect our cities, cement's journey from quarry to construction site is a testament to human ingenuity and engineering. As our cities continue to grow and our infrastructure needs expand, this remarkable material will undoubtedly remain at the heart of human progress, just as it has for generations.